Look at your equation sheet. You'll see that it's listed on there. See, so this is our double slit right here. And notice I get the expression for bright and for dark spots. And then down here I have the expression for single slit. It looks a little bit different, but I just moved the A over. A sine theta is equal to m times lambda. And then this is the order for our dark spots. And so notice we have dark right here. So you just need to be aware what's on the equation sheet and be able to use it when the time comes. Okay? They work out practically the same, though, as far as the mechanics of finding things like the angle or the width of the slit or the distance between the fringes. Let's try this one. You have the green line of a gaseous mercury, like you guys did in the lab, the spectroscopy lab, where you have different colored lines for hydrogen or helium, or in this case mercury. And the green line falls at 546 nanometers, that's its wavelength, and it falls on a single slit apparatus, and then it creates an interference pattern. This is the angle. Now what is the slit width? Alright, let's stop at 155, and we'll go on to 2 minutes. Alright, just a few more seconds. Just guess if you're not sure. Alright. Very good. A is right. So in this, we say A sine theta equals m lambda. By the way, if you ever need to measure something that's very small, this is a great way to measure it. Like if you come upon something you need to measure the width between two objects that are very close together, you can take a laser and shine it on that slit and then measure the interference pattern and very accurately measure very small distances. I mean, this is not that small, but you can measure very accurate distances down to like microns. All right, so A sine theta is m lambda. We're looking for A, so that's m lambda over sine theta. M is the fourth dark fringe, so that means 4. Now if I'm looking at my pattern, I have 1, 2, 3, I'm out at this dark fringe, the fourth one. So 4 times 546 times 10 to the minus 9 divided by sine of 0.092. And that's equal to, what was it, A? Is that the right answer? Yeah, so that's 1.4 times 10 to the minus 3 meters, which is going to be A. All right, let's look at diffraction gratings. I'm sorry, I don't think I have many jokes. Like, I'm almost done, so I'm trying to conserve them a little bit because I fear that I'm going to run out before the end of the semester. All right, let's look at diffraction gratings. Diffraction gratings are work out almost identical to the double slit. In fact, they will work out identical with one small caveat. That when I have a diffraction grating, I'm not going to measure the slit width, or I'll need to know not the separation between the slits, but I have to calculate it in a slightly different way. Most diffraction gratings are made from some transparent material. With grooves etched into the material. I'll pass one around in just a minute. You can take a look at it. The spacing for these grooves is usually defined like this, where you get a number of lines. They're often called lines, or I'll call them grooves, or we can call them slits, but they're usually called number of lines per distance. So for example, on this diffraction gradient I'm going to pass around, it says that there are 1,000 lines per millimeter. So for example, this one that I'll pass around is 1,000 lines per millimeter. And that works pretty well in separating out visible light. So if you've seen diffraction gradients like this, which you might have, or if you've ever used a spectrometer and you've used a diffraction gradient that's kind of like this, it's probably a little fancier. This is just sort of for demonstration, but it's a lot the same as this. It's going to be about 1,000 lines per millimeter. So if we think about this, like in this sketch, this would show sort of a diffraction grating where I have 10 grooves over 1 centimeter of width. So then this one would be defined as having, or described as having 10 lines per centimeter. Sometimes it's per centimeter, sometimes it's per millimeter. You just sort of, or this would be centimeters. Sort of have to be aware of what you're dealing with. So this is 10 lines per centimeter. That's because I have 10 individual grooves etched into this plastic. Usually when they do this, they usually use a chemical process, and they actually have these vertical lines in the plastic. Although sometimes if you're building spectrometers for, say, longer wavelengths, they'll make a diffraction grating, but not out of a transparent material, but out of, say, aluminum or some other metal that you can polish. Okay? I'm going to pass this around. You can take a look at it. I'll work out sort of how this works. But when you get it, sort of look at this at the diffraction grating. Notice that the 1,000 lines per millimeter is written on there. And then you can sort of look at the lights. So sort of take it up and look at the different lights, and you'll see that the colors are spread out into their different colors. So I can see the red and the orange and the yellow and the green and then the blue as you go through. Okay? So I'll pass this around. You can take a look at the lights, and then also just take a look at the diffraction grating. Now to calculate the position, you need to know the distance between the grooves. And so that's different. We need to know this distance, which is our distance d. And in order to calculate that, we say that, well, taking this example, I say 10 lines per centimeter, and I just do the inverse of it, because I want to know the number of centimeters per line. And so that's going to be 0.1 centimeters per line. Now I want to know it in SI units. 0.1 centimeters is 0.001 meters. So with the diffraction grating, whenever you're calculating anything about where the interference pattern is, you'll need to convert your number of lines per centimeter or per meter or millimeter or whatever into meters. Okay, can I go down from here? Is that okay? All right. So you try it on your own. You have this diffraction grating that has 3,000 lines per centimeter. What is the slit spacing for that grating in meters? let's stop at 120, 120. Okay, good. A is right here. I do 1 over 3,000. And that'll tell me the number of centimeters per line, which is really what I want to know, the distance between the slits. And then 1 over 3,000, what was the answer? Okay, 3.3 times 10 to the minus 4, thank you. That's in centimeters though, so the right answer, I moved that decimal place over 2 places, is going to be 3.3 times 10 to the minus 6. Let's see, we're doing oldie but goodie. Hey, where did the farmer meet his wife, or get his wife? Y'all remember? I told you this last semester. He tracked her down. That's a good one. Okay. Fraction gradient shows the same diffraction pattern as a double slit apparatus. It was exactly the same. Once you get past calculating that distance d between slits, it works out exactly the same as the double slit. Exactly the same. So d sine theta is equal to m lambda. This gives us our bright spots. And m is equal to 0, 1, 2, and on and on. Let's try this question. But first, actually, I'm going to work through this with you because it kind of brings up an important point. So I have this diffraction gradient that has 12,000 lines per centimeter. First of all, I need to find d. d is 1 over 12,000. That's in centimeters. Which is 8.3 times 10 to the minus 7 meters. I'm going to invert it into meters. It actually comes out 8.3 times 10 to the minus 5. I just move that decimal place over twice to get it in meters. And now I want to know the number of bright spots. So I say d sine theta equals m lambda. Now we haven't done this yet, but let me posit to you that if I have a double slit, I'm going to draw it as a double slit because it's easier to just draw 2 slits, but it's the same for diffraction gradient. When I have a double slit, I get a single. When I have a double slit, I get a central bright fringe followed by these fringes all along the way. I mentioned this early on, but I measure this angle theta right here, and it increases up to a certain amount. The angle theta will increase up to 90 degrees. So theta has to be something less than or equal to 90 degrees. And so what we do here is we find out what is the order number when theta is equal to 90 degrees. So we say d, which is 8.3 times 10 to the minus 7, times the sine of 90, because 90 degrees is the limit for where my interference pattern can form, times m, times lambda, which is 436 nanometers. And then I solve that for m rather. And I get 1.9. So m is equal to 1.9. Now how many orders then do I get? For theta equal 90 degrees, my m is equal to 1.9. Theta cannot exceed 90 degrees, so what is the maximum number of orders that I get on I just get 1. I round this down. I never round it up. I round it down to the nearest integer. So the maximum number of orders is 1. Or is m equal 1? Now let's go back and ask this question. It's asking how many bright spots are on the screen. So if I think about my interference pattern, I have the 0th order, and then I have the 1st order. All right, and that's a lot like the one that I showed before, that I get my 0th order right there, and then I get my first orders, and I don't really have the second order because you just can't. I just don't get the second order. It doesn't exist. Okay? So how many bright spots do I have on the wall up here? I have 3, right? I have the 0th order, and then I have the 2 first orders to either side of it. So the answer to this one would be D3. Okay, so be prepared to deal with double slit or with diffraction gratings. The only difference there is calculating the distance between the slits. But then once you do that, it works out exactly like a double slit. Look at the homework, look at the old test for practice on that. But they'll look a lot like this. I could ask you also what is the distance between the fringes like we've done before. So, what is this distance, y? But it works out exactly the same way. Everything's the same as the double slit. Yeah, Brittany? Okay, all right, so it's an important point. Let me make sure I recap. It's really, you have to read the question carefully here. So it says how many bright spots are on the screen. So we calculated the maximum order number. Using theta equal 90 degrees, I find that the maximum order number is 1.9. But I round this down to the nearest integer because theta can't exceed 90 degrees. So my order number is not going to go to 2. Like the angle has to be greater than 90 degrees for this to be 2. So I round it down to 1. So the maximum number of orders in this is 1. But the question is asking not what's the maximum order, but how many fringes there are on the screen. And so here, for example, this also has a maximum order number of 1. I have my central bright spot, and then I have a bright spot on either side. Okay? Is that clear? A little more clear? Y'all okay with this? Yes? No? How y'all feeling? Okay. Practice it. We can return to it, but you'll practice it on your own and try it out. Let's see. Fresnel bright spot. This occurs in other places as well. You can get diffraction in all sorts of scenarios. And a Fresnel bright spot just occurs, like let's say that you have some round thing and you shine a light onto it. This is a flashlight. I'm shining light onto it. It experiences diffraction as well. And what happens, you get a diffraction pattern that looks a lot like this, where it doesn't just cast a shadow, but instead you get a bright spot here in the middle. This is called the Fresnel bright spot. With dark and bright fringes that go along the way. And the reason that is it's sort of like a double slit where you have these light waves that are now propagating outward from either side of this thing, this aperture that's blocking light coming along. Okay? So just know that this exists. You may or may not see a question. If you do, it'll probably be just something like this one, like a figure, and I just ask you what has caused this pattern. And what has caused this pattern, by the way? Is it a laser beam on a single slit? No, right? It's not on a double slit. It's actually going to be light incident on a circular object, such as a penny. Just know that that exists, that these other types of diffraction occur. They can occur in other geometries, but the idea is still the same. Light travels, and it travels at different path lengths. See, I think that's the end of that chapter. We have a few more quicker questions. All right, let's try this one. You have another diffraction reading that? I have that other one. Okay, I'll get that in the class. All right, let's stop at 55. Okay, awesome. B is right. If I want to make the pattern narrower, A sine theta equals M lambda. That means if I want to make theta decrease, then I have to increase the slit width. And that's sort of counterintuitive. Like you would think if you made that slit wider, that it would make the pattern wider, but that's not true. It actually makes it narrow, or makes it move together. Right here. With blue light, I get a diffraction pattern. What if I use red light? What do I have to do to the slit width to recreate that same pattern that I have with blue light? For different wavelengths, diffract differently. All right, let's stop in 50 seconds. 50. Okay, good. D is right. I think that's right. Let's double check. So I have A sine theta equals M times lambda. I'm doubling the wavelength because I'm going to red light. And in order to do that, I have to double the slit width in order to make it the same. Those things are proportional to one another. All right. What do you get here? All right, let's stop at 30, and we're going to keep going, okay? We have about 5 minutes, okay? So we'll move on to the next chapter, so don't pack up just yet. I'll stop at 40. Okay, good. D is right. I get a bright spot. That's that other type of interference, or the interference, the Fresnel diffraction. I'm not trying to just cram in all sorts of stuff, but I think that we'll probably finish this class before the end of the semester, and if that's the case, then we just won't come to class. So that's why I want to push on into the next chapter, okay? So, because if y'all don't have to come, then by all means, don't come. So let's go on to the next chapter. We haven't done sound before. Well, we did do sound actually last year, but in years past we haven't done a lot of sound. So it's an important chapter though, especially for some of you pre-med students. There's a lot of sound on the MCAT, or the MCAT changes every time you take it. So sometimes there's sound on the MCAT, and they're a little bit different, sort of the way we deal with sound waves. But we have lots of different types of waves, right? We have mechanical waves, like waves in water. These are mechanical waves. We have sound waves, light waves, slinky waves. Lots of different types of waves. Waves are periodic, they repeat. And they are called, because they're called periodic waves. This means as they travel through space and time, that they repeat one after the other, or they repeat themselves over and over again. All sound waves are periodic. In some way, or at least at some level. They might be periodic over very long distances, or they might just be periodic on very short time scales. So like, for example, even a clap is a periodic wave. That sound generated has a very periodic function to it. We have two different types of waves, transverse waves. In transverse waves, the medium moves up and down. Whereas in longitudinal waves, the medium moves side to side. So I always like to think of this as, I don't know, like the wave at a football stadium. Y'all ever do the wave? That would be like a transverse wave. So y'all want to try it? So we'll do here, and then as I move across the classroom, we'll create a transverse wave. Are you ready? Y'all are not very good. Okay. That's very good. All right, but now I think that we should really do this at football stadiums. That instead of using transverse waves, that we should do longitudinal waves. And so now instead of putting your hands up, you're going to reach out and you'll hug the person next to you. It will be like a hugging wave. It's a longitudinal wave. All right, y'all ready? So when I go here, you'll reach over and hug the person next to you. Yeah. So that would be a longitudinal. Nice, thank you. So a longitudinal wave, the medium moves side to side. Whereas in a transverse wave, we'll stop there, y'all. But yeah, I'll see you on Wednesday.